This video is going to cover infectious disease modeling, just an overview of what it is and what it looks like. It's not going to be about how to actually carry it out in like a statistical program. So this is what an epidemic might look like plotted out. Where on the y-axis here we have the proportion of a population that's infected at a given time. And you'll notice that it's not symmetrical. It starts out with no one infected, rises very rapidly, and then is much slower as it starts to kind of peter out. And these are some of the other variables you'll see plotted out. And that includes the number that are susceptible, and you'll see that that is decreasing rapidly early on, kind of mirroring the infection one. And the number that are recovered, it starts off a little bit after the infection and kind of rises as basically this infection number infected is decreasing. So basically, similar to what I was describing with people getting kind of boxed in and not able to infect anyone, that's kind of described by this like mass action theory in chemistry. And the kind of principle of mass action is that the rate of a reaction is a function of how much reagent there is. Where when it's not very concentrated, there's fewer collisions happening. Let's just say yellow and blue is reacting to make green. There's fewer of these collisions happening per second when the concentration is lower. When the concentration is super high, it will basically, this reaction will, more reactions are happening per second. This is simplified. What's actually happening is something more like this, where this is just the box full of where this reaction is taking place, whether it's like a gas or a liquid. But they're just moving around in random space, and each encounter of blue and yellow is a chance for a reaction to become green. So early on, there's just so many yellows for a blue to run into and so many blues for a yellow to run into that there's a lot of reaction in that first 5 minutes, and a lot of reagent has become product. But there's fewer opportunities now for a blue to encounter a yellow or vice versa. So after 10 minutes, the change is modest, and after another 5 minutes, so 15 minutes in total, the change is kind of negligible. It'll eventually react completely, but as the concentration of reagent decreases, the number of collisions happening per second, and hence the number of reactions just starts to decrease. This is really similar to what's happening in a population during like an epidemic. So this is a really concentrated population. So similarly to the molecules, more interactions per second, or more interactions per whatever time period. And if this has a very like clustered and very infectious situation, then we'll have like a very short spike and a fairly quick dissipation. But if everyone is really spread out, there's going to be fewer contacts per unit time, and this epidemic will have a very different shape. So now in the context of SIR models, compartmental model is another kind of term used to describe infectious disease modeling, or at least a certain kind of it. And it relies on the idea that there's three compartments, S, I, and R, that are susceptible people, infective people, and recovered people. They're three mutually exclusive states that a person can be in. So people are susceptible, they've never had the disease, and they're eligible to become diseased. They move into the infected group at a predictable rate that, like I was talking about, the mass action is a function of how many susceptible people there are. And people who are infective is a term that is used to describe the idea that from the moment someone is infected to the moment they're no longer infected, they're contagious during that whole time period. That's not necessarily true, but that's sometimes like a assumption that's made. And people are moving from this infective group to the recovered compartment at a predictable rate that, with mass action, is a function of how many people are in this compartment. So this is a closed compartmental model. I'm going to talk about open ones after, but with a closed population, the major assumptions are no one's coming in or out, so no immigration or emigration, and no births and deaths. So as far as what's used to actually define these rates, the rate of change from the S to the I compartment is defined by CPI, so the contact rate, transmission probability per contact, and incidence of the disease. And people moving from the I to the R compartments is a function of recovery rate, and that's just 1 over the duration of infectiousness. So some other assumptions before we move forward are that you're contagious for the entire duration of infection. Sorry, I guess I already talked about that. And also transmission is direct from infected to susceptible people, so there's no like vectors or more complicated routes of transmission. So depending on the different features of the disease, so I already alluded to some of them here, like contact rate, transmission probability, just based on some of these different features, these 3 functions, so like this epidemic infectious disease model will look quite different depending on what these parameters are. So this is, for example, R naught, the number of people an infected person goes on to infect. So if it's a high R naught, it'll tend to look like this. It'll start quick and then blow itself out over a like longer period of time, but still relatively quickly. A low infectiousness disease, so like a low R naught, will have a different look. So not if with this other one, everyone got infected over like at some point in the epidemic. But this is a situation where the number that's infected is just kind of this small little bump. So susceptible doesn't even make it all to 0. Like there's still some remaining susceptible people. Another feature is like another way to formally describe what I've been talking about with mass action is just the idea of effective R naught. So effective R naught is R naught multiplied by the fraction that are susceptible. So with this view of R naught, it's the infectiousness of the disease, like this R value, is changing and becoming lower as the number of susceptible people decreases. Another feature of closed models and closed populations is that it all like the epidemic always runs its course. You'll notice that the number or proportion infected always got to 0 in both of these situations. But now we're going to talk about open compartmental SIR models, and just some notation. This plus is for births and immigration, and this minus is for deaths and emigration, and both are considered kind of constant in a population. So this is what the open compartmental SIR model would look like, where we have people still moving susceptible, infective, and recovered, but for each of these, there's the opportunity for people to immigrate in that state, or emigrate or die in that state. And because there's an inflow of susceptible people, and we can look at that inflow as basically like fuel for the epidemic. Since like an open population has that inflow, they can reach equilibrium states, where you can see that the number infected didn't reach 0 ever, and it looks like it's kind of stabilized. And that basically explains how endemic diseases occur. And endemic means like it kind of either seasonally happens or is always kind of at a constant low level rate in the population. So some other considerations with compartmental models, and after this is just a little bit of a summary, but after this I'm going to describe with an example a little bit of how this is actually carried out with like simulations and how it's applied. But some other considerations are not everyone has the same risk of transmission. So if we're looking at HIV, different subgroups are going to have a different probability of transmission, and depending on the route of transmission, if we have like a subgroup that's injection drug users and a subgroup that's like sex workers or something, they might be worth considering separately in this compartmental model, as some of these parameters like probability of infection and contact rate might differ. Emigration might not be constant. We definitely saw that with like COVID, where like the shutting down of borders and stuff probably led to some pretty interesting effects in the transmission of other diseases that aren't COVID. People aren't molecules, so the mass action principle relies on people kind of behaving ideally, randomly interacting. People don't interact randomly. You have like a core group that you meet with every day. You might be very geographically separated, but you come to the same place. It gets pretty complicated. Also, this idea of becoming recovered and then like you're permanently now no longer susceptible. That's not the case for every disease. Some diseases have the ability to basically come back. Like you can get a cold twice. Also, infective is not a very realistic assumption just because there's usually like a pretty specific subset of the disease pathogenesis where you're contagious. So, like I was mentioning before, this function, so these three functions, I guess, are basically defined by some parameters that are either disease specific or population specific. So, things like probability of transmission, duration of illness, and contact rate, which I put under disease specific, but I guess that's more of a population one. And some other features of the population, like the initial number of each of these people, like the susceptible, infected, and recovered, and the inflow and outflow. So basically, if you have each of these, if you have all of the different parameters that describe this, you can either create it, or if you have just this, you can derive the parameters. So this is what people typically have following an outbreak. So they have information on who's in each category over time. So like this is just a little epidemic where everyone's susceptible and the number infected goes up, number recovered lags behind, and you can kind of see how you might be able to get some of those values from that. Um, Basically, you can input that into software, and the software can run a bunch of simulations where they kind of play around with the different values that describe these functions, figure out the one that fits the data best, and then you can use that to derive some of those parameters about the disease that you might not have known before. Like the R naught, how infectious it is, the probability of transmission per contact, disease duration. Those are all things you might not have had before, which is kind of interesting. And it's kind of similar to regression, where the regression is taking this data and trying to come up with the parameters that are the combination of parameters that is most likely to describe the data you gave it. It's a very similar process. So this is Berkeley Madonna. This is basically what it takes to create these lines is calculus, and this is all of the information. These are all the different parameters that go into these lines. What this is basically this curve that I was already showing you before. Colors are different. This is the susceptible people going down over time, infected, and I think this is colonized for C. But as you can see, some of these parameters, like if we start to mess with the duration of infectiousness, this line is going to change quite a bit. Like just depending on if we change contact rate, you're going to get very different probability of infection. You're going to get very different figures each time, basically. And how this how this like why I'm showing you this is that's basically what these simulations are. Like when I showed you before how like a statistical program could do a bunch of simulations and pick like the best one. This is what it's doing. Like it's going through these different combinations of the parameters and finding the one that fits the data best.